So now that we've gone through the mathematical analysis of Young's double-slit experiment, let's actually apply the equations that we've learned. So we have blue light. It has a wavelength of 460 nanometers, and it's incident on two slits that are 0.55 millimeters apart. So we want to find the angle of diffraction for the third antinodal line. Right, so we know our wavelength for blue light. We're told it's 460 nanometers, or 4.60 times 10 to the minus 7 meters. We're told that the distance between the slits is 0.55 millimeters, and of course we can convert that to units into our meters. So that's going to be 5.5 times 10 to the minus 4 meters. And we want to find the angle of diffraction for the third antinodal line. So we're going to set n equals 3. Now, antinodal, this is the bright spot. So this allows us to use the equation for constructive interference, which is the one that's on the data sheet to begin with. So with that said, on our data sheet we have this lovely equation for constructive interference. It says that lambda equals d sine theta over n. Now our interest is to get the angle of diffraction. So the angle of diffraction, sine of theta, it's going to be this n lambda over d. And that's kind of the equation we looked at in the last video when we were trying to relate that path length difference to that angle we made up in that distance between the slits. This is kind of where we started at and then worked our way to this. Now, at the end of the day, I don't want sine of the angle. I prefer the angle itself. So we're just going to take the inverse sine of both sides, which means that the angle is going to be the inverse sine of n lambda over d. Make sure that lambda and d are in the same units. I would prefer to just put them both in meters. N doesn't have any units. And then the only other thing that you got to watch out for, make sure that your calculator is in degree mode. Radian mode, the only class you're going to use radian mode in high school is Math 30-1 and maybe Math 30-2. But for sure Math 30-1. We don't use that pesky radian mode in physics. So let's have a look here. Let's just calculate this out. So if I calculate this out, I'm going to get an angle of diffraction of about 0.14 degrees. Now, let me put that into context for a second. What does this actually mean? Well, let's say I have a screen here, and then here's my double slits. So there's my two slits down here. We're told they're distance d apart. Here's kind of my central maximum. N 1, 2, 3, 1, 2, 3. So this is my n equals 0, and this is my n equals 3. This is obviously not to scale, by the way. I should just emphasize that. So what that's saying is that line, that angle that's formed between the midpoint and my central maximum, so this line here, and then that line that joins the midpoint to my third fringe. What they're saying here is that that angle here, that's 0.14 degrees. Now obviously I didn't draw that to scale, that's a little hard. Now you might say, well, let's say I want to measure something like this in a lab. How can I, as a person, measure 0.14 degrees? Like, that's really, really small and probably beyond our measurement skills. You're right, it most absolutely is beyond your measuring skills. What we're going to show you is how to deal with that case, because experimentally, trying to deal with 0.14 degrees, it's going to be a little challenging, but there is a little bit of a mathematical way around that. We are going to show you another mathematical trick. The catch, it has limitations. This equation here already has limitations imposed on it, so the next equation we're going to show you has limitations imposed on limitations. Stay tuned for that.